Now we're going to generalize what we were doing just a little bit more. And this definition requires some discussion. Let S be a solid that lies between x equals a and x equals b if the cross-sectional area of S in the plane px through x and perpendicular to the x-axis is a of x. What? Let's keep going. Where a is a continuous function, then the volume of S is v equals the integral from a to b of a of x times dx. Let's put this in the context of what we've been doing. Here we've got our solid, and it was obtained by rotating the graph of a function around the x-axis. But now what I want to focus on is the disk that we got. There's this idea of the cross-sectional area of S in the plane px through x and perpendicular to the x-axis. Here's the plane in this picture here. Of course, we didn't look at the plane at all, but if we were to take the solid that we got and slice it using this plane, then we would end up with the disk that we were looking at, right? Then the area of the disk is pi r squared, or pi f squared. In the case of the washer, here's the plane that's slicing the solid and giving us the washer, okay? So if a of x is a circle, then we used a disk, and then a of x became pi f of x squared. In the case of a washer, area of x was pi times f of x squared minus g of x squared. This definition allows for the area to be a more general shape. Suppose they are squares or triangles or something more exotic. And we'll see some of that. I want to talk about dimensions though. Area, let's say we're talking about square inches. Area is going to be square inches. And then dx is an incremental thickness that would say also be in inches. And if I multiply square inches by inches, then I'm going to get cubic inches. Now those are units for volume. And what I'm really doing here is I'm emphasizing that dx is a dimension, right? When we were finding area early on in integrating, we had f of x times dx. The dimensions of f of x would have been, say, inches. Inches times inches, square inches, that gave us area. Now we have area times inches, and that's going to give us volume. Well, enough of that. Let's see an example. Find the volume of the described solid S. The base of S is a circular disk with radius r, and parallel cross-sections perpendicular to the base are squares. So this is saying that I've got a shape that's based on a circle at the bottom. I think I want it oriented like that. And then parallel cross-sections perpendicular to the base. What? Here, the parallel cross-sections are circles. Here, the parallel cross-sections are washers, right? So it's what happens when you slice. So we're told that parallel cross-sections perpendicular to the base are squares. So let's just look at a segment that goes across the circle. I know, well, that looks like an ellipse. I know, but it's like, to think about this being in perspective, okay? This is the base of a square. So imagine that that's a square. Again, perspective, right? Let's do that again. It's a square. So at the edge of a circle, it's more narrow, right? Which means that this is less high. And then we can keep going. Now this is going to taper down to a point over here. And then if we connect all the corners, then we end up with this shape. That could be really hard to describe, but I'm going to say it looks kind of like a mohawk. Let's single out one square. This is going to be our slice, just like our disk slice or our washer slice. The only way this will make any sense to me is if we introduce some axes. Now I've laid down some axes here. I think I need to make them thicker. And you'll see the utility of the axes in just a bit. But this circle here is intended to be in the xy plane. So we need to decide which axis is x and which is y. I've given you hints with these arrows, but let's look back here at the definition of area. And the plane is supposed to be through x and perpendicular to the x-axis. And so if I've got a plane that's slicing this square out of this shape, then that makes this the x-axis. And then this is the y-axis. Then I have here a point on the circle. It's got coordinates x, y. This volume is going to be an integral from a to b of a of x dx, where a of x is going to be the area of a square. Now, hang on. If you're paying attention, we're going to integrate with respect to x. And that should make sense, because if we were to rotate this, you would see that a representative rectangle is oriented with a delta x. But the width of this rectangle is 2y, because we're talking about the height, right? The distance from the x-axis. So the area of, I said a rectangle, but it's a square, is going to be 2y whole thing squared, right? It's a square, so this is 2y by 2y. This is single variable calculus, so I can't put a y squared into an integral with respect to x. But this disk is circular with radius r, and so it has an equation, x squared plus y squared is equal to r squared, which means that y squared is equal to r squared minus x squared. So our volume is going to be the integral from negative r to r, the circle has a radius of r, of 2 times r squared minus x squared dx. Whoops, that 2 should be a 4, right? Because I squared 2 and then I squared y. Y squared got replaced by r squared minus x squared. As before, the actual calculus is really straightforward. 4xr squared minus 4/3 x cubed evaluated from negative r to r. And you can verify that we get 16/3 r cubed.